Alright, good afternoon. Two announcements before we start the class. The second example is on next Thursday, next week Thursday, 2:10 to 3:30, next Thursday. What? No.
Is that the final?
25th.
That's all I care about. Probably the balance.
No.
Why not?
Better before hot dog.
No, just no toasted
Oh, do you actually want all of the materials to be on site?
So it's gonna be on the same place that we had Science Center hall. So there are two problems.
We've only covered two topics.
Yeah, two chapters. Chapter 4 and 5. Chapters.
What were they about? What was failure theory? What's the other one?
Deflection,
Deflection.
buckling, and failure theory. Static failure.
Real question.
So this is the first one. Second one, tomorrow we don't have class. So I'm gonna cancel out tomorrow's class. You can drop your homeworks by my office. Or the mailbox. No. What? It's something. At the moment, I don't have any in my mind. Something about sure. Yes. No fatigue. No fatigue. It's chapter 4 and 5. Static failure and deflection. Fatigue is going to be chapter 6.
Yeah, I just got them.
So we saw that 2:10. Mike, this is the first thing. Alright. Let's continue.
At least twice.
No, but like actually. Also, so like the count.
Alright, today we are gonna talk about modification factor.
I have the one. You come with me.
Literally doesn't fit.
It's so
When we talk about SN diagram or fatigue strain, we assume that the component is made of the material that we are looking for, it's fatigue strain. So it's a machine and polish. So first, machine and polish. It's under, it has the standard dimension. And it's completely reversed. Bending moment. Pure bending. So the load that we applied, it was pure bending. It's running at room temperature. By having this assumption, we could find SM curve, which is going to look like something like this for ferrous material. And we define S prime E, which is the endurance limit. The S prime E, based on the experimental data that we had, can be calculated by equation 6.8. So we have this, so we can find S prime E. But now, if we have a new mechanical component, which is going to be different than the test specimen, then S prime E should be modified. So because the new component that we might have, it might be different. It might be different. It might be non-machined or polished, so we should consider that effect. It might have different dimension, so we should modify that. And also we might have different type of the loading. Not pure loading, we might have torsion, torque, or axial load. We should consider that. Also, it might work at a different temperature. So we are going to modify S prime E if these factors are changing. So we define this factor, Ka, Kb, Kc, Kd, Ke, Kf multiplied by S prime E to find the modified endurance limit. So we call the modification factor endurance limit modification factors. Today I'm going to go over these factors. This factor coming from experimental results. So they run the test. They could find Ka and just come out with a new equation to give us Ka. For Kb also Kc, Kd, Ke, and Ka. And you can see what would be Ka to Kf. So I will just start with Ka, which is a surface condition. So it's going to be the first one. There is a equation which is coming from experimental data. Ka is going to be A times the ultimate strain power B. What would be the A and B? A and B would be the parameters depending on surface finish. So table 6.2. If the component that you have is ground and the unit is in kpsi, the A value would be 1.34 and B for both either megapascal or kpsi is going to be negative 0.085. If it's machined or cold drawn, if the surface, if the material has been machined or it's a cold drawn, then you pick the different factor. So based on the type of surface finish that you have, you pick the right A and B. And one thing that you should know about that, suppose S ultimate is 600 megapascal and it's machined. When you want to plug in A, B, and K, SUT, A it's gonna be for machine 2.7. S ultimate, this is the point. You should use S ultimate in megapascal, not change it to the. It should be 4.5. Yes, thank you. So inside the parentheses, don't have 600 times 10 power 6. It should be in megapascal or kpsi if it's in US unit. And power negative 0.0265. 0.265. And find k. And the higher strength material are more sensitive to the rough surface. I mean, you will see from this equation as well. So second factor, we are going to solve example on that, but second factor is size factor. It has many details. KB. First, if the load is axial load. Axial load means something like this, or on compression. If this is the load, KB is always equal to 1. So the size doesn't affect on endurance limits. So KB is going to be 1. For bending moment, and torsion, with rotating and round cross section. So if the cross section of the component is circle and the component is rotating, something like the shaft. So if we have these three conditions, it's rotating, it has a round round cross section, and the load is bending moment or torsion, we are going to use this equation, KB. The diameter, find the range. If it's between 0.11 and 2 inch, use this equation. Plug in D, find KB. If it's between 2 and 10, use that one. Or if it's if you have a SI unit, you can use the last two rows. For bending moments and torsion with non-rotating and or non-circular cross section, we are going to use the same equation, but instead of using D, we are going to define effective D, or DE. So suppose you have a component with the circular cross section, which is under torsion, just pure torsion, and it's not rotating. It's not rotating. You are going to use that equation, but you are going to use effective D, which is coming from equation table 6.3. Table 6.3. For circular cross section with the diameter of the D the effective D is gonna be 0.370 times D. And if you have non-circular cross section like this with E and H, the DE is gonna be 0.808 times the square root of HB. The book has discussed about how to find DE, but we don't go through the details. We are just using table 6.3. Table 6.3, it's gonna have some other cross sections that you can use. I just have these two for either non-rotating and or non-circular cross section. Make sense? All right. Kc is load factor. Ka surface condition. Kb is size factor. Kc load factor. If you have pure bending, it's not gonna affect. It's gonna be same as this one. So it's not gonna change the spring E. So Kc is gonna be 1. But if it's a torsional load or we have bending, axial load, we are gonna use these two factors, 0.85 and 0.59. And as you see, all factors are less than 1. If they are gonna decrease spring E because we are gonna move from the perfect test specimen to the real component, which is not perfect. So it's gonna decrease spring E. Load factor, it's easy. Kb is the temperature. It's easy, just 6. We are going to use this table. As I said, they are coming from the experimental and the test. So table 6.4. Read the temperature. The working temperature is 100 centigrade or 200 Fahrenheit. Then read this column. 1.020. Or if it's more working at 500, it's 0.995. At the room temperature, which is 70 Fahrenheit, it's gonna be 1. Room temperature. So just between 100 to 400, it's slightly greater than 1 because for this range of temperature, the temperature is acting as a heat treatment, so it's gonna increase the endurance limit a little bit, but more than 400, it's gonna decrease. At 1100 Fahrenheit, it's gonna be half. Make sense? Ke is called reliability. So let me look at this graph that I showed you before. And they run the test for the different ferrous material to figure out what would be the endurance limit for the material with the different S ultimate. And they got these points. And they tried to fit a line or curve through these dots. So they come out with this straight with this line with the slope of 0.5. And after 200 kpsi is gonna be 100 for spring. But suppose the material that I have is this one. It's about 130 kpsi. So the test is gonna show me the spring E is about 45. For this material, I'm gonna read SE 45 kpsi. for S ultimate equals to 1/3. I don't have access to the data to the experimental result. I'm gonna have used that equation. 1/3 divided by 2 is gonna be 65, which is gonna be my SE. As you see, there is a significant difference between the actual endurance limit and the value that you can get by applying the equation that we talked about that. So why we have this error? Because we could fit the baseline to the experimental data. So it's a 50% error by fitting this. If you want more reliable design, you can say, I would like to have reliability of 90% or more, 99% or less. So this table is gonna tell you what should be the KE on that equation. If you stick with 50%, meaning you are gonna use the equation that we talked about that, so you shouldn't touch this. But if you want more reliable design, then you have to use the corresponding factor. So 95%, you are going to use 0.868. So when you use 95%, by confidence of 95%, you are sure that SE is going to be KE times S ultimate divided by 2. Which is 0.86, 0.868. So
Why are they doing different? Like from what the stuff that Corey had done, that's KR, so really just a big difference between the two.
between
K and KR for our reliability. It seems like it's a sort of translate between the
Yes.
two topics.
Yep.
Okay.
we are going to use this to design of the other component, but some components they are going to have more details on that each organization is going to have, like the algorithm for the gearbox.
Okay.
Any questions so far? All right.
I got a question.
Sorry.
Where did the divide by 2 come from?
The aspirin E is S ultimate divided by 2. This is what we know from this graph.
So you're just multiplying the K factor
Yes.
by that. That's just to modify that. So the SOT over 2 is just like the S prime.
Here,
You already have it. And then
you remember this?
Yeah.
Based on this data, I can say aspirin E is going to be half of S ultimate if I have a material less than 200 kpsi. So what I'm saying is this equation has 50% reliability. If you want to be more reliable, then you should consider this factor. Because I showed you, for example, for this point, you expect, based on this equation, you expect to have this amount for aspirin E, but in reality it's going to be much lower than that. To address this issue, we introduced K.
Okay.
50% That'll work out.
Any questions so far? All right. KF is addressing the other factors that you might see on the component. We don't go through that in this course, but they exist. Depending on the situation that you have, you may need to go to the handbooks and find the corresponding modification factor. So let me work on one example. It's on the slide. Example 6.8. We have a material AISI 1015. It's hot rolled. It has been machined, the material has been machined. It's under fully reversed axial load. So the load is axial at temperature of 550 Fahrenheit. So we have this situation, it's working at this temperature, it's under fully reversed axial load. Fully reversed, I mean force is varying like this, P as a function of T. If it's non-reversed or if it's not fully reversed, we are going to look at it next week. So far, whatever we covered, we assume that we have fully reversed cycle. What we see is failure after 50,000 cycles.
$50 or $70?
70, sorry. If the reliability is 99%, estimate the endurance limit and fatigue strength at this cycle. So is that clear? All right, let's start. It's made of 1015 hot rolled. So table A20, I'm gonna show you where you can find the data that you need for your design or analysis. Table A24, it's gonna have the strength of the material for the steel. So 1015 is here, hot roll. It has S ultimate of 340 megapascal or 50 kpsi, and the yield strength of 190 megapascal and 27.5 kpsi. So let me use the US unit. So table A24, S ultimate is 50 kpsi. And I'm just writing yield strength as well. But then I'm gonna start from this equation. So aspirin E. First of all, aspirin E. Aspirin E is gonna be the half of S ultimate if it's less than 200 kpsi. So less than 200, which is the case, we are going to use the half of S ultimate. Half of 50 is going to be 25. So if I had the test specimen under those conditions, I could stop here and say endurance limit is 25. But I should consider these factors because we don't have the perfect condition. I will start with Ka, which is surface finish. So Ka is A times S ultimate power B right here. It's machine, so 2.7. I'm using kpsi, 50 kpsi, negative 0.265.
So it
Zero.
says it's machined, but it also says hot roll, like in the
Machine or
Western
cold
statements,
drawn.
but we're not cold
But
drawn.
it's hot roll material that has then been machined. So you get
So
your
you pick
you
the
get your
most
SY.
recent.
We are
No, no,
using
so
this.
Yes, you get
Okay.
you get your strength from the fact that it's 1015 hot roll, because hot roll has a different strength.
Yeah.
But then afterwards it says it has been machined. So it's that material has been hot rolled, but then you have a surface finish, so it's the machining surface finish.
All right. Let me.
Say if you were like some hot wool versus cold drawn.
Yeah, they're two
That's what I just-
materials. So that's the material you start with, but then you machine it afterwards, and that will give you surface
So,
finish.
so what that factor is a surface.
Yeah.
So you can still have a hot.
It's something they love.
So it's being machined. Because that because if you don't surface it.
So if you just if you said just 10 hot roll and it doesn't say has been machined, so 10 hot roll
So
says
just say put it together
Just like
like
make it
a link out of steel, and you just take a steel bar that's been hot rolled, and then the surface finish is hot rolled. But it's just a surface.
I guess
it's
this is a good explanation if we say hot roll is for the material before doing the surface finish. So I stick with that. I mean, hold on. So what I'm saying is the material can be cold drawn, but when you are doing the surface finish, you can do the hot roll after that for the surface finish. So saying that I stick with machine because it's just representing the material, no matter what would be the surface. So 0.9575. KB is the load factor. If the load factor is axial load, KB is 1, so we don't change KB. It's an axial load. KC is the size factor. Sorry, KC is the temperature factor, load factor. For axial load, I should use 0.85. Equation 626. KD is the temperature, so the working temperature is 550. In this table, we have 500 and 600. So 550 would be at the middle. I just made an average. So KD is gonna be KD for 600 plus KD for 500 divided by 2. .979. Add them up and divide it by 2. Endurance limit, reliability factor for 99%. For 99% is 0.814. Now, time to find SE. SE would be KA, which is 0.975, KB1, KC is 0.85, KD is 0.979, and KE is 0.814 times aspirin E, which is 25. If I do the math, I will get 16.27. So from 25 kPSI to that 16.27. This is the first part. Second part. For the ferrous material, which still is one of them, we have 1 million, which is occurring at 1 million, and the other one, this point is 1,000. So it says we are gonna see the failure at 70,000 cycles, meaning it's gonna be between 1,000 and 1 million, somewhere here. So basically we are in this region. What is the equation of this? It's gonna be SF for fatigue strength equals to A and power B. If you recall. From previous class. A and B for that one can be obtained by these two. So let me just find A. It's a F, fatigue fractions. Table of figure 618. Fatigue fraction. F. So Fs ultimate is square divided by SE, not S print E, SE. So what would be the F? I should look at the S ultimate. S ultimate here is 50. So the range of this figure is 70. So I consider that as a 0.9. So for S ultimate equals to 50 kPSI, F would be 0.9. So 0.9 times 50 kPSI
So would you just use 0.9 for anything less than 70?
Yes.
Or I guess 70 or less?
Yep, less than 70, yep. So again, 0.9 times 50 kPSI should be 10 power 3. S E is 16.27. We get 119,000. 119. Or 190. Just 190. No, it should be 10 power 2. Or 119 kPSI. And B is negative 1/3 log of Fs ultimate 0.9 times 50 kPSI divided by SE, which is 16.27 kPSI. We get negative 0.141. So we are given with N, we would like to find fatigue strength at that number of cycles. So SF would be 119 PSI, 70,000 power negative 0.1414. So fatigue strength is going to be 23.9 kPSI. So for this number of cycles, the fatigue strength is going to be this. If I gave you the the area of the cross section, you could find the load applied to this, because we know that it's gonna fail at this number of cycles. At this number of cycles, the fatigue strength should be this. So sigma would be F divided by 8 for axial load. If the cross section is given, you can estimate how much force we apply to the component. Any questions so far? So the next topic that we are going to cover is the effect of stress concentration factor on fatigue problem. On chapter 3, if you remember, we just introduced stress concentration factor when we have discontinuity on the component like this, the actual stress, which is sigma max, it's greater than the theoretical stress, which is coming by dividing force dividing by the cross section. So we define KT on that chapter. And we learned how to find KT by using the table A15 for the different loading and the components. And here, for the static loading that we covered on chapter 5, the concentration factor should be ignored on ductile material. But for dynamic loading that we have on fatigue problem, we should look at KT, which is fatigue, which is stress concentration factor. So it's the reason that we need to study fatigue concentration factor in chapter 6. I define two factors, KF, fatigue concentration factor for normal stress. And KFS, S representing shear stress, so fatigue concentration factor for shear stress.
Stop. Some material are fully sensitive to KT. So what do I mean by fully sensitive? I mean fully sensitive to KT. It means KF is exactly equals to KT. Whatever value you got for KT on the table A15, not table, figure. Appendix. You can introduce as a KF, but some other material are partially sensitive to KT. So for those material, KF would be 1 plus Q KT minus 1. This Q is representing the sensitivity of that material to KT. Fully sensitive means Q equals to 1. Fully sensitive. Q equals to 1, just plug in 1. KF would be 1 plus 1 times KT minus 1. KT is going to be equals to KF. Partially sensitive, Q is going to be less than 0. No sensitive, Q equals to 0. KF equals to 1. If it's not sensitive to fatigue concentration factor, KF is going to be equal to 1. So whatever stress you find, you can use that one. For example, here, force of P is going to apply here. Suppose here I have one hole in the middle. So the nominal stress is P divided by A. Area is going to be this area. But the actual stress is going to be sigma times KF. Fatigue concentration factor should be considered to find the actual stress applied for doing the analysis. So next Monday, we are going to talk more about this factor. I will collect the homework tomorrow. You can drop it in my office, but I will post a new homework. What is the new homework you're doing?
Monday.
not this coming Monday, after the exam.
Oh, no.
Thursday weekend, come on.
We can change it to Thursday if you want.
Will stuff that's on the homework be on the test?
No,
No,
the
okay.
homework is gonna be the fatigue.
Okay, awesome. So test has nothing to do with the game.
Chapter 4 and 5. Chapter